First nice property. I can prove things with this. You've presumably all had to write a two-column proof once in your life. They suck. But I can write out two-column proofs entirely with first-order logic. That's nice. One thing in particular, no infinitely long proofs, right? That would really suck. If you had to prove something that the proof was infinitely long. Anything I can prove in a finite number of steps. Maybe a lot. Maybe it takes me 400 pages to prove something. But it's never going to take me an infinite amount of time to prove something. If I can prove something at all, I can prove it in a finite amount of time. That's called compactness. Believe it or not, that's not always true. Some of the first examples of logical systems stronger than first-order logic are not compact. And you need to use infinitely long proofs to prove anything. This sucks. If you ever hear me slam my head against the wall screaming, second-order logic, why the fuck do you have to be like that? You'll know why now. Second-order logic is not compact.
But can you abbreviate? Can you be like,
You
if
can.
X, Y, Z, equals, and parentheses.
Sometimes. There's a thing called the computable fragment of second-order logic, which is the part that you can abbreviate. You can't abbreviate enough of it, though. What you can abbreviate, it turns out to be, is just first-order logic. So you get these nasty circles. You take something that's really powerful, but it's no longer compact. Okay, look at the part you can't abbreviate. Oh, fuck, we just got first-order logic again. It's very irritating. The second point that first-order logic has that's really nice is a little weirder. And the problem with this one is people thought it was a bad thing rather than a good thing. Compactness everybody likes. There is nobody who's kept awake at night thinking if only we had infinitely long proofs. At least I hope there's nobody who's kept awake thinking that. Macy, stay with infinitely long proofs.
It was him.
You want infinitely long proofs?
Not really.
Enough that you have your manifolds. Why do you want to have manifolds in long
I only
proofs?
want infinite long proofs so I can impose them on other people.
Basic symbolism.
I will state the full version, actually not completely, of Lowenheim's goal. So, this will take some explaining. Note that I use Greek letters. Greek letters automatically signify that I'm doing logic, and it's thus completely irrelevant to anything else.
That's money different, right?
Bad economist.
No.
Go
Give him a
down.
weapon. Why did you give him a weapon? Stop it.
Hey, you can write on your girlfriend after the lecture.
Alternatively, our lecturer could write on his girlfriend during the lecture.
He's already writing on Matt. That would be
Yeah.
redundant. Carry on.
This glorious woman.
Well, according to his desk, she's also a tempestuous lover.
Yeah. Oh, that's the best case scenario.
According to this one, she calls and doesn't put out.
Okay, she's got me. Why would I want to try anyone?
No.
Okay, so, oi! So,
Okay.
start with a set 5 of countably many sentences. I'll explain why we need that in a second. True somewhere. This somewhere kind of died because I wonder why. But this says true somewhere. What do I mean by that? I have my sentences. There's some structure in which they describe something that's actually going on. There are some sets of sentences that are true nowhere. Example, exists X, exists Y, so there exist two things, and not exists X, exists Y. There are not two things. These two sentences are never true at the same time. So this would not be a set of sentences I'm considering. This dies. A horrible, painful death. But suppose that my set of sentences can actually all be true at the same time. The term used is consistent or satisfiable. I'm going to use consistent. Neil will want me to use satisfiable. Here's the weird part. Maybe phi is true only in very, very, very large structures. Right? I put no limit on how big my structure is. The Lowenheim Scholem says that phi is true in some countable structure. In essence, there's two ways to interpret this. Either, whenever I want to talk about something too big, I'm fucked. That's the bad way. Or, all I need to completely understand first order logic is countable things. That's the way it's actually useful. It's not useful for using first order logic to prove other things. It's useful for proving things about first order logic. Again, you have absolutely no reason to believe anything I just said. The examples are not very helpful and take a lot more first order logic that really sucks. Neil can explain to you why basic first order logic really, really, really sucks balls and makes everyone want to die. But trust me, this is actually useful. It wasn't thought that way initially. In fact, one of the two guys who discovered it, Skolem, called it Skolem's paradox, and used it as an argument to abandon first order logic forever in favor of, guess what, second order logic. But luckily, he died and his theories with him. So,
Ouch.
two good problems, compactness and long Skolem. No infinitely long proofs, and no need to go too large in terms of structure that we look at. One bad property, not very strong. Question, is there a logical system that is strictly stronger than first order logic and still has these two nice properties? That's the question that Lindstromprt theorem answers. It'd be really great if there were, right? Because then we could prove things with it because of compactness. It wouldn't be too complicated to understand because of long Skolem, and it'd be strong, so that'd be excellent, and then we switch over to it. The fact that we're still using first order logic suggests that nobody's ever found such a stronger system. For about 40 years, people kept trying to invent really strong logical systems. L omega 1 omega, second order logic, L infinity, which is badly behaved in more ways than I can literally count. Fixed point logic, stationary logic, I only know what a few of these mean. Ramsified logic, logic with cofinality quantifiers. I've been reading about these recently. Lots of them. Those are actually really cool. They all were either not compact, or didn't have low Skolem, or lost both of these at the same time, and just really sucked. Second order logic, by the way, does not have low Skolem either. Second order logic sucks balls. And second order logic is unfortunately what I'm actually interested in. I might be found behind a refrigerator someday.
Decision.
The chicken.
Well,
Eat it for the chicken.
Noah, did you just use
I will
square
come
logic for
and
that?
shove the fucking chicken down your throat.
And then comforting.
Isn't it nice to have helpful friends?
Well,
I'd fly it for you.
no. This is all I have in common with Leroy Jenkins, by the way. At least I'll have chicken.
Wow.
Someone throw something in here.
I have all the chalk. I mean, very good.
No, John.
Oh,
Not the chair, not the chair.
no. No.
Let's move on.
All right. First of all,
Maybe better.
everybody keep your shoes on. I'm not the president.
Yeah, I wouldn't throw my shoe at you. That would just
And
be
you're
so
not
early.
you're not in Jordan anymore.
That's
Okay.
Not in Jordan anymore.
Okay.
But usually
Okay.
semantically when we say the president, we mean the current sitting
Speaking of
president.
semantics, how about semantics of second order logic?
Go for it.
Speaking of semantics, Lindstromp's theorem.
Right.
Speaking of semantics, how about I slit my throat?
What?
Haruka!
That's not semantic.
You said semantics is the second
Okay, guys,
order of
math.
logic.
Everyone, shut the
Boy.
hell up.
The timers come from that.
So, unfortunately, it took me a lot longer to get to Lindstromp's theorem than I thought. There's a problem here. There's a lot of logic behind Lindstromp's theorem. By the way, feel free to walk out at any point because I have no idea how long this is going to take. Hopefully, I'll wrap it up in the next half hour or so, or 10 minutes, ideally. So, Lindstromp's theorem. We're fucked. That's basically the statement of Lindstromp's theorem. I mean, it's not a happy theorem. It says that anything that extends first order logic loses one of these nice properties. How the hell do I go about proving something like that? First, no. And no.
Oh.
First, think about how complicated something like this is to prove in the first place. Right? It's not a theorem about natural numbers, or sets of natural numbers. All the mathematics, meta-mathematics, meta-meta-mathematics, meta-meta-mathematics, dot, 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 on that hierarchy, I don't know exactly where I put Lindstromp's theorem, but it's somewhere fairly high up. I think 6 or 7 metas, actually. Neil and I worked this out at one point, I can't remember what we got exactly. It's pretty high up the meta hierarchy. So it's insane that this can actually be proven. But it can't. It's actually a straightforward mathematical theorem. Proved just with, you'll love this, first order logic. At the end, there will be philosophy.
Isn't that somewhat
Yeah, I was gonna
At
say.
the end, there will be philosophy.
Yeah, that doesn't. Okay.
Oh, at the end, you can take apart everything I've said about Lindstromp's theorem. That's the fun part. So, what I spent 8 months trying to figure out how the hell to do was prove this damn theorem. Because nobody can write Lindstromp's theorem to save their life. I'm not really sure why. It has a smiley face. It is awesome. Here's the idea.